electrons of mass m with the de-Broglie wavelength lambda falls on the target in an X-ray tube. The cutoff wavelength lambda naught of the emitted X-ray is. So you have to find out the cutoff wavelength of this X-ray tube lambda naught in terms of incident wavelength lambda. The electrons are incident. So now kinetic energy of emitted electrons or kinetic energy of the electrons which are falling, kinetic energy of electrons falling on X-ray tube is K is equal to P square by 2m. Correct? I told you this. Kinetic energy is momentum square by 2 times the mass. Okay? Now, by de-Broglie's hypothesis, since lambda is h by p, p can be written as h by lambda. So that is by de-Broglie's hypothesis. De-Broglie wavelength is lambda is equal to h by p. So K should be written as, instead of p I will substitute h by lambda divided by 2m. So kinetic energy of the electrons falling on the X-ray tube is h square by 2m lambda square. H square by 2m lambda square. This is equation 1. This kinetic energy will be the energy by which photon can be emitted from the X-ray tube. So electron falling on the X-ray tube may emit the photon. This is a X-ray tube, may emit the photon out. So for that, the maximum energy of the photon is hc by lambda naught. That is the threshold one. So the energy that should be due to the kinetic energy of the electrons. So this energy is the energy of the photon for it to be emitted out of the X-ray tube. That will come from kinetic energy of the moving electrons. So when I substitute hc by lambda naught equal to h square by 2m lambda square. Now I have to find lambda naught where h and h cancels here. So lambda naught is 2mc lambda square by h. Lambda naught is 2mc lambda square by h. Out of the given options, option A appears to be the right answer. Option A appears to be the right answer.